The comet arrives from a direction that points toward the constellation Draco, though it began its journey long before that pattern of stars existed in Earth's sky. 3. Atlas carries within its nucleus the frozen breath of molecular clouds that collapsed and reformed while our own solar system was still a disk of swirling dust. Astronomers detect its presence as a faint smudge of light that moves against the fixed stars, betraying motion that speaks of origins beyond Neptune's orbit, beyond the Kuiper belt, beyond the comfortable boundaries of what we call home. The discovery comes through automated sky surveys that scan the heavens with patient precision, digital eyes that never blink, cataloguing every point of light that dares to shift position against the cosmic backdrop. Its trajectory curves through space with the mathematical precision of gravity's invisible hand, following orbital mechanics that were written into the fabric of space-time 4.5 billion years ago. The visitor moves at 17 kilometers per second relative to our Sun, a velocity that carries the signature of interstellar space too fast for our solar system's gravitational embrace, too purposeful to be mere cosmic accident. Only took 46,000 years to cross from Alpha Centauri's distance. If it had come from there, which it did not, the actual journey spans millions of years through the cold emptiness between stellar neighborhoods, a migration so gradual that the cosmic background radiation itself has cooled during the passage. Stars have been born and died while this wanderer drifted through the void, carrying its cargo of frozen chemistry between worlds that may never know of each other's existence. The comet's coma expands as solar radiation warms its ancient surface, releasing molecules that have remained frozen since before Earth's oceans formed. Water vapor, carbon monoxide, and organic compounds stream away in the solar wind, creating a tail that points away from the sun with the reliability of a compass needle. These same molecules once drifted through the interstellar medium, part of the vast inventory of chemistry that fills the apparent emptiness between stars. The tail stretches across millions of kilometers of space, visible to telescopes as a gossamer thread that catches starlight like morning dew on spider silk. Solar photons push against the liberated gas and dust with gentle persistence, sculpting the tail into graceful curves that record the history of the visitor's approach to our star. Spectroscopic analysis reveals the presence of hydrogen cyanide, formaldehyde, and methanol, simple molecules that form the building blocks of more complex chemistry. The visitor carries these compounds like a cosmic seed bank, preserved in ice that has never known the warmth of a nearby star. Scientists wonder whether such interstellar wanderers might serve as messengers, carrying the raw materials of chemistry from one stellar neighborhood to another, connecting distant worlds through slow exchanges of matter that unfold across geological time. Each molecule tells a story of nuclear fusion processes that occurred in stellar cores that died before our sun ignited its first hydrogen flame. The chemical signature speaks of star formation regions where massive stars lived brief, brilliant lives before exploding as supernovae, scattering their nuclear products into space where they condensed into the building blocks of new worlds. The comet's nucleus rotates once every 7 hours, a leisurely spin that speaks of gentle formation processes in the outer reaches of some distant stellar nursery. Its surface reflects only 4% of the sunlight that strikes it, darker than charcoal, darker than the deepest ocean floor, darker than the volcanic glass that formed when lava meets ocean. This darkness comes from organic compounds that have been processed by cosmic radiation during the visitor's million-year journey through interstellar space. creating complex carbon chains that astronomers recognize but cannot fully explain. The surface temperature hovers near absolute zero, warmed only by the distant sun's fading influence as the visitor approaches perihelion. Complex hydrocarbons coat the nucleus like a primordial tar, protecting the pristine ices beneath from the harsh environment of space. Radio telescopes around Earth turn toward the visitor, listening for any artificial signal that might betray technological origin. But the cosmos returns only the whisper of natural processes, the gentle hiss of molecular transitions as frozen gases sublimate into the vacuum of space. The silence itself becomes meaningful, a reminder that intelligence, if it exists elsewhere, operates on timescales and in ways that render our brief attention spans nearly irrelevant. Only took 65 million years since the last mass extinction to produce creatures capable of detecting interstellar visitors. Yet the visitor itself has wandered for perhaps 1,000 times longer. Radio waves from Earth's earliest television broadcasts have travelled less than 100 light-years into space, a whisper that has barely begun its journey to the nearest stars. While this ancient wanderer carries no such technological fingerprints, the comet's composition matches theoretical predictions for objects formed in the outer regions of protoplanetary disks, where temperatures remain low enough for volatile compounds to condense directly from the gas phase. Water ice dominates the nucleus, but embedded within this frozen matrix lie trace amounts of more exotic molecules: ammonia, hydrogen sulfide, carbon dioxide, each compound a fossil record of the conditions that existed during planetary formation around some distant star. The ratios of these molecules provide clues about the temperature and radiation environment of the visitor's birthplace, allowing astronomers to reconstruct the characteristics of stellar systems that may no longer exist. Deuterium ratios in the ice reveal the cosmic history of the hydrogen atoms, tracing this journey from the primordial nucleosynthesis that occurred 3 minutes after the Big Bang through billions of years of stellar processing. Gravitational perturbations from Jupiter and Saturn gradually bend the visitor's path as it passes through the inner solar system, demonstrating how massive bodies shape the trajectories of even the most distant wanderers. The comet's orbit becomes slightly bound to our Sun's influence, though it will eventually escape back into interstellar space, carrying with it trace amounts of material from our own stellar neighbourhood. This gentle exchange of matter between star systems continues throughout the galaxy, a slow mixing process that homogenizes the chemical composition of the interstellar medium across billions of years. Only took 4.5 billion years of galactic rotation to distribute the heavy elements forged in stellar cores throughout the disk of the Milky Way, creating the chemical foundation for rocky planets and organic molecules wherever conditions permit. The visitor's approach stirs something ancient in human consciousness, the recognition that Earth exists within a vast community of worlds, connected by invisible threads of gravity and chemistry that span the gulfs between stars. Organic molecules detected in the comet's coma match compounds found in Earth's earliest rocks, suggesting that the basic chemistry of life may be distributed throughout the galaxy, waiting in frozen archives that drift through the darkness until stellar warmth awakens their potential. Scientists measure isotope ratios that reveal the nuclear processes responsible for creating the visitor's constituent atoms, tracing their origin back through generations of stellar death and rebirth. The same carbon atoms that form complex molecules in the comet's nucleus once resided in the cores of massive stars, where temperatures exceeded 100 million degrees and nuclear furnaces forged the elements essential for chemistry and life. The mystery deepens as researchers discover that the visitor's trajectory cannot be explained entirely by gravitational forces, Subtle accelerations suggest that outgassing from the nucleus creates a gentle rocket effect, propelling the comet along a path that deviates slightly from pure orbital mechanics. This phenomenon, observed in other comets throughout our solar system, hints at the complex interplay between solar radiation and surface chemistry that governs the behavior of these ancient wanderers. Only took millions of years of cosmic ray bombardment to alter the surface composition of the nucleus, creating reactive sites where solar heating triggers the release of gas jets that act like miniature thruster engines. The delicate balance between incoming solar energy and outgassing creates a feedback loop that adjusts the visitor's trajectory with a precision that would be remarkable if it were intentional, but remains purely the result of physical processes that operate without purpose or design. The visitor carries within its frozen heart the memory of stellar nurseries that existed when the galaxy was younger, when spiral arms swept through different configurations and the sun had not yet begun to shine. Deep within the nucleus, beneath layers of processed organic compounds and cosmic dust, lie pristine ices that form directly from the collapse of molecular clouds in regions where massive stars were being born. These ices preserve the isotopic signatures of their birthplace like a cosmic fossil, recording the temperature and density conditions that existed in the interstellar medium billions of years ago. Molecular hydrogen, the most abundant molecule in the universe, once filled the vast spaces between newborn stars in the visitor's home system. In the cold depths of these molecular clouds, temperatures dropped to just 10 degrees above absolute zero, allowing complex chemistry to proceed at rates so slow that individual reactions might take centuries to complete. Carbon monoxide molecules adhered to tiny grains of silicate dust, building up layers of ice over millions of years while the cloud gradually contracted under its own gravity. The visitor's nucleus contains these ancient ice mantles, preserved through eons of wandering in the even colder depths of interstellar space. Heavy water, containing deuterium instead of ordinary hydrogen, tells the story of cosmic nucleosynthesis with particular clarity. The ratio of deuterium to hydrogen in the visitor's ice differs subtly from the proportions found in Earth's oceans, suggesting formation in a region of the galaxy where the interstellar medium had been processed through fewer generations of stellar evolution. Only took 13 billion years for the universe to evolve from primordial hydrogen and helium to the rich chemical complexity preserved in this wandering ice ball. Scientists wonder whether the deuterium enrichment they observe reflects conditions in the early galaxy, when star formation proceeded at a more leisurely pace, and the interstellar medium retained more of its primordial composition. The visitor's trajectory through space carries it on a path that intersects with the orbital plane of the solar system at an angle of 28 degrees, suggesting it approached from the direction of the constellation Lynx over the past several thousand years. This geometry provides clues about the motion of the Sun through the local interstellar medium, as gravitational focusing effects would tend to concentrate the arrival directions of interstellar objects toward the solar apex, the direction of the Sun's motion through space. The visitor may have been traveling through the local bubble, a cavity in the interstellar medium carved out by ancient supernova explosions, for hundreds of thousands of years before encountering our solar system's gravitational influence. Amino acids locked within the visitor's icy matrix await detection by increasingly sophisticated analytical techniques. These organic compounds, if they exist, would represent the products of interstellar chemistry that proceeded in the absence of liquid water or planetary surfaces. Formaldehyde and hydrogen cyanide, already detected in the comet's outgassing, serve as precursor molecules for more complex biochemistry, suggesting that the basic building blocks of life may be synthesized routinely in the cold depths of space. The visitor becomes a time capsule, carrying samples of the organic chemistry that existed in its birth system before planets formed and biological evolution began. Radio telescopes detect the characteristic frequencies of water masers naturally occurring laser emissions in the expanding coma of gas surrounding the nucleus. These masses form when water molecules become excited by solar ultraviolet radiation and emit coherent radio waves, creating cosmic lighthouses that can be detected across vast distances. The phenomenon occurs only under specific conditions of density and temperature, providing a sensitive probe of the physical environment within the comet's atmosphere. Scientists use these massive signals to map the three-dimensional structure of the gas flow, revealing how solar heating creates complex patterns of sublimation across the nucleus surface. The mystery of the visitor's origin deepens as astronomers trace its trajectory backward through time, following its path through the gravitational influences of nearby stars. Computer simulations suggest the comet may have been ejected from its parent system during a close encounter with a passing star, an event that would have disrupted the outer regions of the planetary disk and sent countless small bodies on trajectories that carried them into interstellar space. Only took a few million years for such gravitational interactions to empty the outer regions of a young planetary system, scattering its most primitive components across the galaxy like seeds on cosmic winds. Isotopic analysis of noble gases trapped within the visitor's ice reveals the signature of cosmic ray exposure during its interstellar journey. Helium-3, produced by the interaction of cosmic rays with heavier nuclei, accumulates at predictable rates in materials exposed to the harsh radiation environment of space. The concentration of this isotope provides a cosmic ray exposure age that may span several million years, suggesting the visitor has been travelling through interstellar space since before the last ice age on Earth. The same cosmic rays that created these isotopic markers also processed the surface chemistry of the nucleus, creating the complex organic compounds that give the visitor its characteristic dark appearance. Thermal infrared observations reveal that the nucleus rotates in a complex tumbling motion, rather than the simple spin exhibited by most solar system comets. This chaotic rotation suggests the visitor experienced significant impacts or gravitational torques during its formation or subsequent evolution, creating an angular momentum state that has persisted across millions of years of interstellar travel. The tumbling motion affects how solar heating is distributed across the surface, creating asymmetric outgassing patterns that contribute to the gentle rocket effect observed in the comet's trajectory. Only took a few large impacts during the early history of its parent system to impart the rotational energy that still governs the visitor's motion today. Spectroscopic observations detect the emission signatures of CN radicals and C2 molecules in the visitor's coma, products of the photochemical breakdown of more complex carbon compounds under solar ultraviolet radiation. These reactive species survive for only brief periods in the space environment before being destroyed by further radiation or dispersed by the solar wind. Their presence indicates active chemistry occurring in real time as the visitor approaches the Sun, transforming pristine interstellar materials into the reactive intermediates that characterize cometary atmospheres. The abundance ratios of these species provide clues about the parent molecules from which they derive, offering insights into the organic chemistry preserved within the nucleus. The visitor's approach to the Sun creates a natural laboratory for studying the interaction between interstellar materials and stellar radiation. As the nucleus warms, sublimation proceeds in order of volatility: first carbon monoxide, then carbon dioxide, followed by water ice, as temperatures rise above the freezing points of these compounds. This sequential release creates a changing composition in the coma that maps the thermal structure of the nucleus interior, revealing how heat conducts through the low-density ice and dust matrix. Scientists monitor these compositional changes to understand the physical properties of materials that formed under conditions vastly different from those found anywhere in our solar system. The organic compounds detected in the visitors' outgassing match molecules found in dense molecular clouds throughout the galaxy, suggesting that interstellar chemistry produces a relatively uniform inventory of carbon-based compounds wherever physical conditions permit. Methanol, formaldehyde, and more complex species represent the products of gas phase reactions that proceed even at the extremely low temperatures and densities characteristic of interstellar space. Only took billions of years of cosmic chemical evolution to create the rich molecular diversity now preserved in wandering comets that carry samples of this chemistry between stellar systems, connecting distant regions of the galaxy through slow but persistent material exchange. Complex organic molecules drift through the vast emptiness between stars with a patience that exceeds human comprehension, travelling distances so enormous that light itself requires years to traverse the same paths. The visitor carries within its nucleus an archive of this interstellar chemistry, carbon chains that form through reactions occurring over millions of years in the tenuous gas that fills the spaces between stellar systems. These molecules assembled slowly, one atom at a time, in environments where densities remain 1 trillion times lower than the best vacuum achievable in terrestrial laboratories, yet where time itself becomes the catalyst for chemical complexity. Polycyclic aromatic hydrocarbons, detected throughout the galaxy by their characteristic infrared emission signatures, likely coat the visitor's nucleus in microscopic layers that accumulated during its journey through the interstellar medium. These ring-structured carbon compounds form through high-temperature processes in the outflows of dying stars, then survive for millions of years in the radiation-harsh environment of space. The visitor's dark surface reflects their presence, organic compounds that began as stellar atmospheres, cooled to form soot-like particles, and eventually adhered to the growing nucleus during its formation in some distant molecular cloud. Only took the death of multiple generations of massive stars to create the carbon-rich dust grains that served as condensation surfaces for the visitor's primitive chemistry. Methanol molecules preserved within the comet's ice tell stories of surface chemistry that occurred on tiny dust grains floating through space at temperatures near absolute zero. In these conditions, hydrogen atoms stick to grain surfaces long enough to migrate across their crystalline structures, eventually encountering carbon monoxide molecules to form the methanol now sublimating from the visitor's nucleus. This grain surface chemistry proceeds through quantum mechanical tunneling effects, allowing reactions to occur despite energy barriers that would prevent them under normal terrestrial conditions. The visitor becomes a messenger carrying samples of chemistry that operates according to rules that differ fundamentally from the warm, dense environments where life as we know it evolved. Radio observations detect the emission lines of numerous organic molecules in star-forming regions throughout the galaxy, revealing a cosmic chemistry that produces remarkably similar inventories of carbon compounds wherever physical conditions permit. Formic acid, acetaldehyde, ethanol, and even amino acid precursors form routinely in molecular clouds, suggesting that the basic chemical building blocks for complexity exist throughout the universe. The visitor's composition matches these observations, indicating that it formed in a typical star-forming environment where organic synthesis proceeded according to universal physical laws rather than unique local conditions. Cosmic rays, high-energy particles accelerated by supernova shock waves and other violent astrophysical processes continuously bombard interstellar dust grains and ice mantles, driving chemical reactions that would be impossible under gentler conditions. These energetic particles break chemical bonds and create reactive radicals that recombine in new configurations, building complex molecules through pathways that bypass the energy barriers encountered in conventional chemistry. The visitor's nucleus bears the signature of this cosmic ray processing in the form of unusual isotopic ratios and exotic organic compounds that could only form through high-energy reactions occurring over millions of years of exposure to the galaxy's most powerful radiation sources. The magnetic fields that thread through the interstellar medium influence how charged particles and ionized molecules move through space, creating pathways for chemical transport that connect regions separated by hundreds of light years. Molecular ions, formed when cosmic rays strip electrons from neutral molecules, follow these magnetic field lines as they drift through the galaxy, carrying chemical information from star-forming regions to the cold depths of interstellar space. The visitor may have incorporated materials that traveled such magnetic highways, collecting chemistry from multiple regions of its parent molecular cloud system before gravitational collapse concentrated these diverse components into the nucleus we observe today. Scientists wonder whether the complex chemistry preserved in interstellar comets like the Visitor might serve as a vector for distributing the chemical prerequisites for life throughout the galaxy. The same molecules that form spontaneously in molecular clouds, hydrogen cyanide, formaldehyde, ammonia serve as starting materials for the synthesis of amino acids, nucleotide bases, and other biochemically important compounds when exposed to appropriate energy sources. Only took 4 billion years of evolution on Earth to transform simple organic molecules into living systems. Yet the raw materials for this transformation may have been distributed throughout the galaxy long before our sun began to shine. The visitor's trajectory carries it through regions of space where the local interstellar medium varies in density and composition, creating a natural experiment in how small bodies interact with their cosmic environment. As the comet passes through denser regions, it accumulates additional material on its surface, while passage through more tenuous regions allows solar heating to strip away loosely bound compounds. This ongoing interaction between the visitor and its environment continues to modify its composition, even as it travels through our solar system, demonstrating how interstellar objects serve as both carriers and collectors of cosmic chemistry. Deuterium fractionation in the visitor's organic molecules provides clues about the temperature history of its formation environment. At the extremely low temperatures characteristic of dense molecular cloud cores, chemical reactions preferentially incorporate deuterium over normal hydrogen, creating isotopic ratios that differ significantly from those found in warmer environments. The enrichment of deuterium in certain molecules within the visitor's nucleus suggests formation temperatures below 20 degrees Kelvin, conditions that exist only in the coldest, densest regions of star-forming molecular clouds. These measurements allow astronomers to reconstruct the thermal conditions that existed in the visitor's birth environment billions of years ago. The silicon-to-carbon ratio in the visitor's refractory components reflects the metallicity of its parent molecular cloud, providing information about the stellar nucleosynthesis history of its birth region. Stars that formed earlier in galactic history produced fewer heavy elements, resulting in molecular clouds with different chemical compositions than those observed in the present-day galaxy. The visitor's elemental ratios may preserve signatures of this early chemical evolution, offering a window into conditions that existed when the galaxy was younger and star formation proceeded under different circumstances, only took billions of years of stellar death and rebirth to establish the chemical gradients now observed across the galactic disk. Yet individual objects like the Visitor carry records of earlier epochs, when these gradients had different values. Infrared spectroscopy reveals absorption features attributed to carbonaceous compounds that have been processed by millions of years of cosmic ray bombardment during the Visitor's interstellar journey. These spectral signatures match those observed in the diffuse interstellar medium, confirming that the Visitor has indeed travelled through typical interstellar environments, rather than remaining in some protected cosmic harbour. The gradual alteration of surface chemistry by cosmic radiation creates a patina of complex organics that tells the story of the Visitors wandering through space, recording the cumulative effects of exposure to the galaxy's background radiation environment. The mystery deepens as scientists detect spectral features that cannot be attributed to a known molecular species, suggesting the presence of organic compounds that may be unique to the extreme conditions of interstellar space. These unidentified features appear in both absorption and emission, indicating complex chemistry that has no terrestrial analogue. The Visitor carries within its nucleus an alien chemistry that formed under conditions that cannot be replicated in any earthly laboratory chemistry, that emerged from the marriage of cosmic time and cosmic emptiness, creating molecular architectures that may represent entirely new categories of carbon-based compounds. Only took the universe 14 billion years to evolve the conditions necessary for such exotic chemistry. Yet each interstellar visitor carries samples of molecular diversity that remain largely unexplored by human science. The solar wind encounters the visitor like a gentle but persistent archaeologist, stripping away layers of material that have accumulated over millions of years of interstellar wandering. Charged particles streaming from the sun's corona interact with the neutral gas surrounding the comet's nucleus, creating a complex plasma environment where electromagnetic forces sculpt the expanding coma into elegant structures that reveal the hidden architecture of solar influence. The wind carries away molecules at rates measured in kilograms per second, each departing atom carrying with it the chemical signature of processes that occurred in stellar systems that may no longer exist. Hydrogen ions from the solar wind collide with water molecules sublimating from the visitor's surface, initiating a cascade of chemical reactions that transform pristine interstellar ice into an active plasma environment. These charge exchange reactions occur with cross-sections large enough to affect significant fractions of the outgassing material, creating populations of energetic neutral atoms that escape the comet's gravitational influence at velocities exceeding the local escape speed. The solar wind becomes a cosmic mass spectrometer, sorting the visitor's constituent molecules according to their mass and charge, dispersing them into space along trajectories that record the electromagnetic conditions encountered during the comet's approach to the Sun. Ultraviolet radiation from the Sun photodissociates complex organic molecules in the visitor's coma, breaking chemical bonds that survived millions of years in the cold depths of interstellar space. The products of this photochemistry, atomic hydrogen, oxygen, carbon emit characteristic wavelengths of light that allow astronomers to map the three-dimensional structure of the gas envelope surrounding the nucleus. Each photon absorbed represents the destruction of a molecule that may have formed in the atmosphere of a dying star, carried through space as part of the visitor's chemical cargo, only to be unravelled by the energy of our own stellar companion. The magnetic field embedded in the solar wind drapes around the visitor's ionosphere, creating a magnetosphere in miniature that channels charged particles along field lines extending millions of kilometers into space. This magnetic interaction creates conditions analogous to those found around planets, but on vastly smaller scales and with plasma densities that vary by orders of magnitude as the comet's outgassing rate responds to changing solar heating. Scientists observe these magnetospheric phenomena as natural experiments in plasma physics, revealing how electromagnetic fields organize matter and energy in environments that bridge the gap between planetary and interstellar conditions. Ion tail formation proceeds through processes that strip electrons from neutral molecules, creating charged species that respond directly to electromagnetic forces rather than the gravitational and radiation pressure effects that dominate dust grain dynamics. Sodium atoms, liberated from silicate minerals within the visitor's nucleus, become ionized by solar ultraviolet radiation and subsequently accelerated by the solar wind's electric field to velocities approaching 100 kilometers per second. Only took a few hours of solar wind interaction to accelerate these ions from rest to speeds that carry them far beyond the comet's immediate vicinity, creating a trail of charged particles that extends along the visitor's orbital path. The solar wind's density and velocity vary with the 11-year solar activity cycle, creating time-dependent boundary conditions that affect how efficiently the visitor sheds its accumulated interstellar material. During periods of high solar activity, enhanced particle fluxes and stronger magnetic fields compress the visitor's atmosphere, increasing collision rates and accelerating the chemical processing of outgassed molecules. Conversely, during solar minimum conditions, the gentler solar wind allows the visitor's coma to expand more freely, creating different conditions for the photochemical and plasma processes that govern the fate of liberated molecules. Cosmic ray particles, traveling at nearly the speed of light, penetrate deep into the visitor's nucleus where they trigger nuclear reactions that produce radioactive isotopes and exotic particles. The solar wind partially shields the inner solar system from the lowest energy cosmic rays, creating a heliospheric boundary that modulates the flux of these energetic particles. As the visitor approaches the Sun, this cosmic ray modulation affects the rate of nuclear processing within its interior, subtly altering the isotopic composition of materials that will eventually be released through sublimation and outgassing. Mass spectrometry of the visitor's coma reveals isotopic ratios that differ from solar system values, confirming the interstellar origin of its constituent materials while raising questions about the nuclear processes that created these distinctive signatures. The oxygen isotope ratios suggest formation in a stellar environment with different nucleosynthesis yields than those characteristic of our Sun's birth region, while nitrogen isotope enrichments point toward processing in molecular cloud environments where chemical fractionation proceeded under conditions not found in the contemporary solar neighborhood. Only took billions of years of galactic chemical evolution to create the isotopic diversity now preserved in interstellar wanderers like the Visitor. The solar wind's interaction with the Visitor creates bow-shock structures analogous to those found upstream of planetary magnetospheres, but scaled to the much smaller dimensions and lower densities characteristic of cometary environments. These shock fronts accelerate particles to energies sufficient to excite characteristic atomic transitions, creating emission features observable at radio and optical wavelengths. The shock geometry responds dynamically to changes in solar wind conditions and the visitor's outgassing rate, providing real-time information about plasma processes occurring in an environment that serves as a natural laboratory for space physics research. Sublimation from the visitor's nucleus follows the inverse square law of solar heating, with outgassing rates that increase dramatically as the comet approaches perihelion. This thermal response strips away approximately 1 meter of surface material during each passage near a star, exposing progressively deeper layers that preserve increasingly ancient chemistry. The current approach to our Sun represents just one of many such encounters the visitor may have experienced during its millions of years of wandering, each stellar encounter removing another thin layer of accumulated interstellar material and revealing older components of its chemical archive. The solar wind carries isotopic signatures of nuclear processes occurring in the Sun's core, allowing scientists to compare the visitor's composition with that of our own stellar environment. Helium isotope ratios in the solar wind reflect the nuclear burning history of our Sun, while trace abundances of heavier elements reveal the galactic chemical evolution that preceded solar system formation. The visitor's contrasting composition provides a reference point for understanding how stellar nucleosynthesis yields vary between different regions of the galaxy and different epochs of cosmic history. Scientists monitor the visitor's response to space weather events, solar flares and coronal mass ejections that temporarily enhance the solar wind's particle flux and magnetic field strength. These transient phenomena create natural experiments in cometary physics, revealing how rapidly the visitor's atmosphere can respond to changing boundary conditions. The plasma environment around the comet reorganizes on timescales of hours to days following major solar events, demonstrating the dynamic coupling between stellar activity and the behavior of interstellar visitors. Only took 4.5 billion years of stellar evolution to create the complex magnetic and particle environment that now governs the visitor's interaction with our Sun. Yet each moment of this interaction reveals new aspects of the fundamental physics that governs matter and energy throughout the cosmos. Gravitational choreography unfolds across the solar system as the visitor's trajectory bends through the invisible architecture of planetary masses, each world contributing its subtle influence to the dance of orbital mechanics that governs motion throughout the cosmos. Jupiter's immense gravitational field, 2.5 times more massive than all other planets combined, creates perturbations that extend far beyond its immediate vicinity, shaping the paths of objects that pass within hundreds of millions of kilometers of its orbit. The visitor feels this influence as a gentle but persistent acceleration that deflects its trajectory by fractions of a degree, changes that accumulate over months of approach to create significant alterations in its ultimate path through the inner solar system. Saturn's rings and moons generate their own gravitational harmonics, contributing smaller but measurable effects to the visitor's motion as it passes through regions where these influences remain detectable above the background noise of solar system dynamics. The mathematical precision of these interactions follows Newton's inverse square law with unwavering fidelity, creating predictable changes in the visitor's velocity vector that astronomers can calculate centuries into the future. Only took 300 years since Newton's Principia to develop the mathematical tools necessary to predict such gravitational interactions with sufficient precision to guide spacecraft trajectories. Yet the same physical laws have governed celestial mechanics since the formation of the first gravitationally bound structures in the early universe. The visitor's hyperbolic trajectory carries excess velocity that exceeds the escape speed from the solar system, ensuring that its encounter with our stellar neighborhood represents only a temporary deflection rather than permanent capture. This interstellar velocity reflects the motion of the visitor's parent star system relative to our own, preserving information about stellar kinematics that existed millions of years ago when the comet began its journey through the galaxy. Gravitational focusing effects concentrate the arrival directions of such interstellar visitors toward the solar apex, the direction of the Sun's motion through the local interstellar medium. creating an observational bias that affects the apparent distribution of these objects across the celestial sphere. Tidal forces from the Sun begin to deform the visitor's nucleus as it approaches within a few astronomical units, creating stresses within the ice and dust matrix that may trigger fracturing and fragmentation events. The differential gravitational acceleration across the comet's diameter remains small compared to its internal cohesive strength, but even tiny tidal effects can exploit existing weaknesses created by thermal cycling, cosmic ray bombardment, and the mechanical stresses of rotation. Scientists monitor the visitor's light curve for evidence of such structural changes, watching for brightness variations that might indicate the exposure of fresh surface material or the creation of dust clouds from mechanical disruption. The three-body problem emerges as the visitor's trajectory becomes influenced simultaneously by the Sun's gravity and the perturbations from major planets, creating a dynamical system that exhibits sensitive dependence on initial conditions. Small uncertainties in the comet's position and velocity, arising from measurement errors and unmodelled forces like outgassing-induced accelerations, grow exponentially over time through the chaotic dynamics of gravitational interactions. This mathematical sensitivity places fundamental limits on how far into the future astronomers can predict the visitor's precise location, even though the overall characteristics of its trajectory remain well constrained by conservation laws. Lagrange points throughout the solar system create regions of enhanced gravitational stability, where small objects can accumulate over astronomical timescales, forming temporary reservoirs of interstellar material that occasionally release their contents back into heliocentric orbits. The visitor's trajectory carries it near several of these dynamically interesting regions, where the combined gravitational influences of multiple massive bodies create complex potential wells and saddle points in the effective gravitational field. These mathematical structures govern the long-term evolution of small body orbits throughout the solar system, creating pathways that connect different dynamical reservoirs and enable the transport of material between distant regions. The visitor's approach, velocity of 17 kilometers per second relative to the Sun, places it near the lower end of the distribution expected for objects arriving from the local interstellar medium, suggesting either an origin in a nearby stellar system or a trajectory that has been significantly modified by previous gravitational encounters. Computer simulations of stellar encounters throughout the galaxy's history reveal that close passages between stars occur frequently enough to alter the velocities of comets and asteroids, scattering them from their parent systems and sending them on trajectories that carry them between stellar neighborhoods. Only took a few million years of wandering for gravitational perturbations to modify the visitor's original velocity, obscuring direct evidence of its birthplace among the statistical noise of galactic dynamics. Planetary protection protocols require careful monitoring of the visitor's trajectory to ensure that its path does not intersect Earth's orbit within the uncertainty envelope of current predictions. The mathematical chaos inherent in three-body dynamics means that small perturbations could potentially alter the comet's path enough to create a collision hazard, though current calculations suggest such scenarios remain highly improbable. The visitor's hyperbolic excess velocity ensures that any hypothetical impact would occur at speeds exceeding 40 kilometers per second, creating kinetic energies comparable to those released by nuclear weapons, even for relatively small objects. Gravitational wave detectors on Earth remain sensitive enough to detect the passage of extremely massive objects through the inner solar system, though the visitor's modest size places it far below the threshold for such observations. The curvature of space-time around the comet follows Einstein's general relativistic predictions with precision that becomes measurable only for the most massive objects or the most sensitive instruments. Scientists use radar ranging and optical astrometry to track the visitor's position with accuracies approaching a few kilometers, sufficient to test relativistic effects and search for anomalous accelerations that might indicate non-gravitational forces acting on the nucleus. The mathematical beauty of orbital mechanics reveals itself in the visitor's trajectory as a conic section, specifically a hyperbola that emerges naturally from the inverse square law of gravitational attraction. This geometric relationship connects the visitor's motion to the same mathematical principles that govern planetary orbits, satellite trajectories, and the paths of binary stars throughout the galaxy. The eccentricity of the visitor's orbit exceeds unity, distinguishing it from the bound elliptical orbits characteristic of solar system objects, while placing it within the broader family of gravitational trajectories that include parabolic escape orbits and the hyperbolic paths followed by interstellar visitors. Gravitational slingshot effects could potentially alter the visitor's trajectory if it were to pass sufficiently close to a massive planet, though current predictions suggest such close encounters remain unlikely during its passage through the inner solar system. The mathematics of such gravitational assists follow the same principles used to accelerate spacecraft to escape velocities, demonstrating how the same physical laws that enable human space exploration also govern the natural dynamics of interstellar objects. Only took 50 years of spaceflight experience to develop the sophisticated orbital mechanics techniques now used to predict the visitor's motion. Yet these same gravitational principles have shaped the evolution of planetary systems throughout the universe for billions of years. The visitor's gravitational influence on other solar system objects remains vanishingly small, too weak to measurably perturb even the smallest asteroids or the most sensitive spacecraft trajectories. Its gravitational cross-section for significant interactions with solar system material spans only a few thousand kilometers, ensuring that direct gravitational encounters with other objects occur with frequencies measured in astronomical timescales. Scientists calculate that millions of years might pass between close approaches to objects large enough to produce detectable gravitational effects, placing the visitor's current passage through our stellar neighborhood within the realm of rare but not unprecedented celestial events that occur throughout the galaxy's billions of star systems. Spectroscopic whispers emerge from the visitor's expanding coma as starlight passes through the tenuous gas envelope, imprinting absorption lines that reveal the precise wavelengths where specific molecules intercept photons traveling across billions of kilometers of space. Each absorption feature corresponds to a unique molecular transition, a quantum mechanical fingerprint that identifies the chemical species responsible for removing particular colors from the background stellar spectrum. These spectral signatures accumulate over hours of telescope